Hello everyone, today I would like to talk about catenary curves and how they can be used to model arches that do not have large bending moments. A catenary curve can be derived from the way how some flexible rope or chain hangs under its own weight, like here. And since we don't have here bending stiffness, there are also no bending moments. And if one inverts this shape, one gets a compression-only arch, which is very effective because the material of the arch gets utilized very evenly. In Grasshopper, there is a component which can be used to directly get the shape of such a catenary using starting point, end point, and the length of the catenary. However, what comes out of this component is not quite exact. It's a polyline which consists of straight line segments. And as we will see later on, a compression-only arch is very sensitive with respect to geometric imperfections. And that's the reason why I exploded this polyline curve and used the vertices here to reconstruct it, a curve which is smoother using this interpolate curve component. I divided the catenary curve into two parts so that I'm able to place here an additional support in the middle, so to make sure that the displacement of the structure is symmetric with respect to this point, and that the catenary is supported in a determined way. In the new version of Karamba, you can feed into a line to beam component not only straight lines but also curved ones. And when it is fed with curved lines, you can use here these three input plugs to define how the curve gets converted into straight line segments. If the line segments are getting smaller than the default snap length of 5 millimeters, then one needs to supply here and here a smaller value. The supports, I'll quickly enable the model view component. Let's take a look at the supports first. They need to be defined in such a way that they point here at the endpoints in the direction of the middle line of the arch. In case we would have transverse support reactions, these would immediately lead to bending moments here. So that's why I use the curve frame component to derive the directions here and orientate the supports accordingly. So we have here support in the direction of the arch curve and here in the plane, in the direction perpendicular to the plane of the catenary. There's one additional support here at the top. One rotational support makes sure that the catenary cannot fall over. The other one is here to avoid rotation about the global y-axis, which is possible because the two support lines here and here meet at one point, and this would be then the point about which the structure could rotate. The loads are placed on the structure using a block load. You can see this here. The orientation is global, which means this uniform line load acts in the same way as that weight. Let's take a look at the deformation of the structure. One can see that it slightly moves here in the direction perpendicular to the arch. The displacements are quite small, and it makes a difference whether we use first or second order theory calculation because of the normal forces in the arch. Since they are compressive, they slightly decrease the stiffness of the arch. The bending moments can be seen here. There are small bending moments because of the deviation between the ideal catenary curve and the approximated structure, which consists here of straight line segments. I can control the approximation of the catenary curve using one of these parameters. For example, this one here. If I make the approximation more coarse, one can see how in the segments we get here this additional bending moments, and if I decrease now this, the error gets smaller and smaller, but doesn't vanish completely. The reason for this is that the arch also is deforming in the direction of the axis, and this leads to this small bending moments. Okay. Now I would like to switch over to the arch modeled as a shell. The geometry is again derived from the catenary component, again somewhat refined using this intermediate step here, and then this curve is used to create a lofted surface. The supports at the starting point and at the end point of the catenary are again oriented in such a way that they point in the direction of the inverted catenary. There's only one support direction blocked here, that's this one. And the second support here in the middle is used to make sure that the structure cannot move as a rigid body in the local y-axis and rotate about the local y-axis. I enabled here dead weight, and one can see first of all here, by taking a look at the utilization of the shell, that the upper and the lower side have nearly the same utilization, and using this shell section component and taking a look at the bending moments in the tangential direction of the cutting line, which goes from here to here, one can again see that the bending moments are very small as compared to the normal forces, which of course depend on the geometry of the catenary. So if it's has a larger height, the normal forces decrease, the bending moments increase. Let's disable the normal forces again. And again, this slight bending moment is due to the fact that the shell also deflects in the direction of the middle axis. And let's see what the effect of the mesh is on the result. So if I have here very fine mesh, we get this result. And of course, in case the elements get larger, we have a more inaccurate result here. That's it. Thank you very much. Goodbye.